So this is the product from the last reaction. So when you dehydrate the water, when it's removed, will form double bond, and so this would be alpha beta unsaturated ketone. And probably the difficulty that a lot of students have in doing these condensation reaction is to be able to redraw. So make sure you form the enolate and know exactly which carbon you're going to make the carbon-carbon bond formation with, and then redraw the starting material, unreacted starting material, and make sure that you're making the correct bond between the nucleophile and the electrophile. And to check that, your product, the Aldol addition product, should always be beta hydroxy carbonyl compound, in which the double bond, when it forms, will be conjugated, so that you could draw a resonance structure. If the double bond is somewhere else, not conjugated, then you probably don't have the right product. All right. So in this case, we reacted the Aldol products from two carbonyl units that have been identical, because it's doing a self reaction. One with the enolate with unreacted carbonyl. But what would happen if we mixed two different aldehydes in a mixed aldol or a crossed aldol reaction? So this is directly from your book, in which is showing what would happen if basically I have aldehyde A with the aldehyde B, and I could have aldehyde A be the enolate and form itself. So I will get, that's this example here, A enolate reacting with A unreacted, and I'm getting an AA dimerization. Or I could get B to form the enolate and react with unreacted B to form BB dimerization. So those are the two possible self-condensation, self-reaction product, addition product that you could get. Or you could have a cross aldol, in which you have the enolate of B reacting with unreacted A to form a B product. Or you could have the enolate of A react with unreacted B, so that you have BA aldol product, addition product. So the upshot of this exercise, which by the way is a great way to practice aldol reaction, is that 4 possible products are going to be forming, and that is not something that you want to do in lab, because if you got all 4 products and they're mixed, you're going to be spending a lot of time separating them, and you know how difficult it is to purify and separate now that you've done some of that kind of research in lab, right? So this is not practical in lab. All right. So there are ways to go around this problem, and one of the ways to go around, if you wanted to do a crossed aldol, so in other words, we don't want to do a self reaction, but we want to react two different carbonyls to try to make the aldol product. Then what are some of the tricks that we could use? One trick is to use carbonyls with no alpha hydrogens. All right, so in other words, how about if we use formaldehyde? as the electrophile. Then we don't have to at least worry about it becoming an enolate and reacting with itself. It could only serve as the electrophile carbonyl, right? Another one is benzaldehyde. Many students would think that there's a hydrogen here, but you know that this carbon already has 4 bonds, so there's no hydrogen there, so there's no alpha hydrogen. So they could only serve as electrophile, these 2 examples, so therefore it can't do a self-condensation product, all right? Second is to either use a strong base, such as LDA, because remember back when we talked about strong base versus weak base, when you use such a strong base like this, you form quantitative enolates only. So in other words, you don't have this problem of having a mixture of enolate along with unreacted carbonyl when you use a strong base. So you could, for example, take whatever carbonyl you want, and you would do this at a low temperature again. And if you have LDA in the flask and you add the aldehyde dropwise to the LDA solution, so that you have more of the LDA than the starting material, then you could form the enolate, and then without having the starting material present, and then you add an electrophile source. In this case, you don't have to be limited to aldehydes with the alpha hydrogen. You could use any kinds of aldehydes. So let's say you react it with cyclohexane aldehyde, then this is going to go and react here and form the product. So you're making a bond between this carbon and this carbon. So that's the bond that you're making, and redraw the carbon here, and that's going to become alcohol, right? And then that is connected to the cyclohexane group. So that would be the Aldol product. So by using a different condition, not using a weak base where equilibrium condition is allowed, if you have an irreversible condition in which it becomes all enolate and then react with another carbonyl, then you could take advantage of the cross aldol and make that happen. All right. Basically, similar thing to that is if you have a compound in which you have more acidic protons, for example this pK of 9, even if you use a weaker base in this case, you know that you're going to form the enolate in the middle between the carbonyl, and then you could react with whatever electrophile carbonyl that you want, and then you could do a crossed aldol as well. All right, so in this case you would have carbon-carbon bond formation with this carbon, and then you have OH forming there, and then you have a carbon, right? So even if this was mixed, notice that the pK of this is 9, but the pK of this is around 20. So the base is going to deprotonate this proton first, so this will be forced to be the enolate, which means that this will be forced to be the electrophile and make this bond, which would be an example of crossed aldol. All right. So at this point, you should be able to do these cross aldol problems in which you are reacting with acetone and benzaldehyde. acetone and formaldehyde. So these are examples where the aldehyde has no alpha hydrogens. And then pentanal and benzaldehyde as well. Those three are examples of that. And then these compounds, notice, are this kind of example where you have a more acidic proton, and then you're reacting with other, these are serving as the electrophile, and these are going to be serving as a nucleophile because they have the more acidic proton. And then you should be also able to do 22.23.